In this little tutorial, we will analyze the robustness of a closed-loop system we have obtained by hand-tuning a PID controller. The system we will design a controller for is a double mass model. So that's a model where we have two masses that move. We can impart a force on one of them, and they are connected through some flexible element. So it might be a flexible shaft or a flexible transmission. And all shafts and transmissions are flexible if you just move the masses fast enough. This is a quite commonly used model for position control systems, for instance. I have plotted the Bode plot of the system here. We see that it's integrating system. The input is force and the output is position. So it's typically a double integrator, but there is some friction as well. So in practice, it's a single integrator. Then we have some resonance here for higher frequencies, and this can create some troubles for us if we want to push the closed loop bandwidth above this frequency here. The PID controller, I will create it using the PID function. And we see I pass three parameters, P, I, and D. The parameters in this case, I have created these sliders that allow us to control these parameters. And the sliders are available in this Pluto UI package. And if you want to see how you create such sliders, it's just a call to the slider function with a range and a default value. And then I create a markdown string where I just insert the sliders. And the reason for that is so I can get this nice LaTeX output. I also create a reference pre-filter. And the reason for this is that if you tune a PID controller so that the step response to a step change in the reference looks good, you typically have very poor disturbance rejection performance. But if you, on the other hand, tune the PID controller so you get good disturbance rejection, then you typically get a way too fast and aggressive response to reference changes. So by including this reference filter, I get 2 degrees of freedom. I can control both the feedback path and the feed forward path from the reference separately, and that allows me to get good performance for both kind of step responses. To simulate this system, I create 2 closed loop transfer functions. Here I have created the loop transfer function, P times C. If I call feedback of the loop transfer function, I get the closed loop system from reference to output, and then I multiply that by the reference pre-filter, so I get the filtered reference step closed loop transfer function. If I instead call feedback P, C, I get the following transfer function, and that's the transfer function from a load disturbance appearing at the plant input to the plant output. And then I concatenate the 2 of them, so I get a closed loop system with 2 outputs. All right, and I plot step responses here. So here we see the response to a step in the reference, and here we see the response to a step in the load disturbance at the input. And I can drag these sliders to change these plots in real time. So we see that if I have a very slow integration, it takes a long time to control or regulate a disturbance step back down to 0. And if I increase the integration time too much, we see that I get poor robustness. But let's say I have tuned this system so that I'm happy. I have maybe selected the filter time constant for the reference pre-filter so I don't get this overshoot you see here. I increase that slightly, maybe say that I'm happy there. Now I'm happy with this simulation performance here, but I have used a model of the system, and that model maybe is derived from first principles. Maybe I have done some system identification to get it. Maybe I have linearized a non-linear model that you have implemented in Modeling Toolkit. No matter how you have obtained the model, it's likely that the model is not perfectly accurate. So I want to make sure that I'm robust in both my stability and my performance with respect to small changes or small errors in the model. So how would I go about analyzing that robustness? Classical control theory tells us that we should look at phase margins and gain margins. And we can do that by creating a margin plot, and we pass the loop transfer function, and we see that on the left here. So we see that we have a gain margin of 18, almost 19, so that's a huge gain margin. And we see we have a number of different phase margins here, and they are plotted in this phase curve. And we see that they're all fairly large. We can also look at the Nyquist plot, so we know that the Nyquist plot is not allowed to encircle this critical point marked in red here, and it doesn't. In fact, it stays quite far away from that point. So that makes us confident that we have a reasonable robustness in our system. But phase margins and gain margins are actually not always very good indicators of robustness, and the reason is that if you have such a loop appearing here in the Nyquist curve, and that loop is actually facing the critical point, it might be inside the unit circle. So where this gain curve crosses the unit circle, you have good phase margin, but you still have a very small distance to the critical point. And the distance to the critical point, the shortest distance to the critical point, happens to be the maximum magnitude of something called the sensitivity function. And you see there are two circles drawn here in this Nyquist diagram. We will get into what these circles represent. This small circle is actually, it has a radius that is related to the maximum magnitude of the sensitivity function. We can obtain the sensitivity function by calling sensitivity on our plant and our controller, and then we call a h infinity norm on that function, and that gives us the maximum value of the sensitivity function. It's around 1 here. If the value is 1, it means that the Nyquist curve never goes inside a circle with radius 1 centered around the critical frequency, critical point. But as the maximum magnitude of the sensitivity function, we see the sensitivity function here, by the way. As that grows, we get peaks in this function. This circle gets smaller. So we want typically this circle to be large, meaning that this function is small, has a small peak. It will always reach, this function will always reach 1 at one point, but we don't want it to shoot above 1 very much. These 4 transfer functions here are sometimes called the gang of 4. We should always inspect all these 4 transfer functions before we determine that we are happy with a closed loop system. We can create this plot by calling gang of 4 plot with the plant and the controller, and here I provide also a vector of frequencies. And the sensitivity function and the complementary sensitivity function T are usually good to look at for robustness properties. This transfer function P over 1 plus PC, it's the magnification of the disturbances happening on the plant input, how they transfer to the plant output. And we see that we reject disturbances over the entire frequency range, and in particular low frequencies disturbances are rejected strongly. This transfer function here, C over 1 plus PC, that is the amplification of measurement noise that appears in the control signal. So it's also important to make sure that we don't get very aggressive control signal action in the response to measurement noise. And we see here that we have in fact quite large amplification of measurement noise here for high frequencies. We see that there is some roll-off for high frequencies here, and that's because I included a, where do we have it? I included a time constant for a filter in the PID controller. So if we increase that time constant slightly, we might see that the roll-off here changes. But if we filter too heavily, we will get worse robustness properties. So if we move on and look in more detail into the sensitivity functions, we see I call here h infinity norm of the sensitivity function. it gives me 1.2, and it appears at this particular frequency. This is related to the phase margin. In fact, this value gives us a lower bound on the phase margin. So the phase margin will never be worse than 48 degrees in this particular case, and we can derive the bound on the phase margin like so, where ms is the maximum peak in the sensitivity function. We can also compute the maximum peak in the complementary sensitivity function. It's given by this value here, and this is the complementary sensitivity function. And we see there are dashed lines appearing in these two figures here, and that's because I have provided a keyword argument ms lines and mt lines, and given the computed ms and mt. So these functions exactly dodge these lines at least one frequency. And we also see in the Nyquist plot here I have provided ms circles and mt circles, and that's because these maximum magnitudes correspond to, they are straight horizontal lines in these plots, but they correspond to circles in the Nyquist plot. So it's generally good to have large radius of these circles, so we stay away from bad behavior. If we stay away from the critical point in the case of this circle, and we stay away from poor robustness and poor step response performance if we are outside of a large circle here. All right. But since I also included a reference pre-filter, it might be interesting to also look at the transfer function when we include that measurement filter. So here we have the gang of 4 plot again, but I actually call something called gang of 7 plot. And it's because there are 7 transfer functions of interest when we include the measurement filter. And we see here that we have the typical complementary sensitivity function in blue, but in green dashed I include a transfer function from reference to output. And this is typically a transfer function we are interested in. And we see that we have more high frequency roll-off now when we include the reference pre-filter, since that's a low-pass filter. We can also look at the transfer function from reference to error. We see that for low frequencies and high frequencies there will be no problem. For these intermediate frequencies here, we actually do have some problem with command following. But if we are happy with the step response simulation here, I don't think this would pose a problem for us. And similarly, this transfer function in dashed blue here shows us the response of the control signal in response to reference changes. To further analyze the robustness, we might calculate something called a Diskmargin. So that is a more modern concept of robustness that allows us to reason about how robust we are with respect to simultaneous changes in gain and phase. So the classical phase and gain margins, they only consider perturbation in either gain or phase. While the Diskmargin visualized here in this figure, it tells us how robust we are with respect to simultaneous changes. So here we see that if we have a gain of 1, or meaning that we have exactly the gain we think we have, then we can tolerate a large difference in phase. We can tolerate, we have a phase margin of above 60 degrees here. But if we have a gain margin, if we have an error in the gain of a factor 4, then suddenly we can only tolerate some 25 degrees of phase variation. And this is, I guess, intuitively reasonable, that if we change both things at the same time, we can't tolerate as much change. We can also visualize the Diskmargins as a function of frequencies. We see that the lowest point on the phase and gain margin appear for a particular frequency here, and for other frequencies we see that we are more robust with respect to gain and phase variations. So I hope that this small example have given you a feeling for if you have a plant model and you have designed a controller, no matter using what method, if you have used loop shaping, or as we did in this case, we just dragged the sliders here a bit so we were happy with the simulation here. we want to verify that we are in fact robust with respect to small changes in the, or small errors in the process model, and those errors will always appear. And to do that, we looked at classical concepts like the gain and phase margins. We visualized them in Bode plots and in a Nyquist plot. But we also looked at the sensitivity functions to verify that those look okay. We computed maximum sensitivities. We showed those in the sensitivity function plot. And then we looked at the Diskmargin to verify that we can handle simultaneous perturbations in both gain and phase. All right, that concludes this little example. Thank you.